So, hello everyone. My name is Vikas Kumar Singh. I am PhD scholar at Indian Institute of Science, and I am taking TA. I am taking class as a TA in the mechanics of metal forming subject as part of my PMRF program. So, this is the third lecture, third discussion on this mechanics of material forming, third lecture, where previously we have discussed two assignment, and now we are going to discuss something related with the theory of failure. And this maximum distortion energy theory has been repeated a lot in the questions. So I was just thinking to give some basic idea about maximum distortion energy theory so that the concept will be clear. And yeah, and this theory is used so many times. So we will start with the basics of theory of failure, and then one by one we will build up that concept, and then we will start with the maximum distortion energy theory. Okay. So first of all, I will tell what is theory of failure. Like in the class, also professor has discussed theory, all this detail, but in the class he has discussed only the main points. So he didn't go in depth of that thing. So I would just like to go in depth for this. Okay. So let's start. So theory of failure. First of thing, whenever we have a member, a static member. So static member is there, and when suppose we are making some structure and all, like suppose we have a cantilever beam kind of thing, and we are putting some load over here. So this is bending like this. Okay. So at some point there is failure in the member. So there is failure, like maybe this will shear up from here, or this will bend and this will fail according to some extra load and all. So whenever a static term is coming, static means a static member structure. You are telling a static structure or a static member. So this whole theory of failure is applicable to a static failure, means a static member only. Okay. Okay. So in this one, basically what we are doing, like basic engineering mechanics, we are using that basic engineering mechanics and developing that theory, and we are coming to the theory of failure using a stress, strain, and all. Okay. So we know like a stress is equal to P by A. P is the load, A is the cross-sectional area. When we are talking about the true stress and strain, so this is the, in the case of true stress, this will be the true area, means instantaneous area, and same in the case of the strain and all. So using stress, strain, Young modulus, G, shear modulus, K, bulk modulus, Poisson ratio, all these parameters, we are developing theory. So, okay. So suppose we have a static member and we are giving some amount of energy in this one, some amount of, I'm telling energy, some amount of energy in the form of stress or strain, whatever, some amount of energy. So this member will fail after some time. Maybe this will break like this. Okay, this will break like this because of this energy input. So what is the maximum amount of energy what we are putting in the system so that the member will be safe? Means I just want to say the limit of this energy so that the energy, this member will withstand that load. In term, see, this energy, input energy will be in the term of stress or strain. Okay, stress or strain. So these two terms, stress and strain, are coupled. Okay, so without the stress, strain will not come, and without strain, stress will not come. So whenever stress is there, definitely there will be a strain. Okay, so now uh, we are talking about, we have in our syllabus we have two type of material. One is ductile material and another one is brittle material. Brittle. In this syllabus we are going to discuss about these two. So for ductile material, researchers have developed different kind of theory, and for brittle material, different kind of theory. So one of the most important theory was a Tresca theory. Tresca. Sorry. Tresca theory. Okay. Tresca. Sometimes it's called Tresca criteria also. And now for ductile material, Tresca theory is there. Von Mises theory. Sorry. What is happening? One Mises theories are there. One Mises. Okay. For brittle material, we have different kind of theory, like more Coulomb theory is there, more Coulomb. Maximum normal stress theory or simply maximum principal stress theory is also there. Maximum principal stress theory, MSPT, or sometimes this is called maximum normal stress theory also. So these all are there. So one by one we will discuss what is this and what is this and all these things. Okay. So when we are talking about the maximum normal stress theory, maximum normal stress maximum normal stress theory, MNST. Okay. So for this, suppose we have three principal stress, sigma 1, sigma 2, sigma 3 in three direction, like 1, 2, 3. I am just taking here. Suppose this is 1, this is 2, and this is 3. Three principal stresses are there. And any one of them, if any one of them is equal to or greater than yield stress, material will fail in that direction. Yield means, suppose you have a stress strain curve. So up to here, this is the elastic limit, and after that, this is a plastic limit. Okay, this is a plastic limit. So suppose this is the yield point for a material, yield point. So before that, whatever deformation is happening, it's elastic deformation, elastic. Okay, and after this means this whole thing is plastic deformation, plastic. So in a static member, plastic deformation should not be there. Plastic deformation means your structure will lose the stiffness, whatever you are designing for, or accuracy. Okay, so plastic deformation means material will deform. Elastically means whatever deformation is coming, when you will remove the load, it will recover the original shape. Okay, so it is assumed like up to here, up to this point, whatever stress you are giving to the material, if that stress is below this, your structure is safe. If it is going above this, you are in the plastic zone, and this is not safe. So all the design, whatever we are designing, we are taking the limit as a yield point, this sigma y. Okay, in all the cases, a sigma y will be the yield point, limit, yield point. Okay, so suppose we have these three principal stresses, sigma 1, sigma 2, and sigma 3, and sigma 1 is greater than sigma 2 is greater than sigma 3. So which one is the highest? This one. Suppose this one. People can write sigma 2 greater than sigma 1 greater than sigma 3 like that also. This all are convenience. That's what. So suppose this is the greatest one. If this value is less than sigma y, means all of these three are less than sigma y, means that a structure is safe. If any one of these three are greater than sigma y, means this is less than any one, sigma 1 or sigma 2 or sigma 3, any one of these is greater than this structure is not safe. It's going to fail. So this is called maximum normal stress theory. So sigma 1, sigma 2, and sigma 3. If this is the thing, so this all should be less than or equal to sigma y for safety. Okay. So this is the uh, principal stress, and I'm just taking sigma 1 and sigma 2 and sigma 3 is the principal stress. Suppose all these three are there, and so what sigma, suppose all these three are there, the sigma 1 is there, sigma 2 is there, sigma 3 is there. So what will be the strain? Sigma epsilon 1 will be sigma 1 by E minus nu by E sigma 2 plus sigma 3. You might be knowing this because when you have a material like this, suppose this is your material. So suppose you have a sorry. Suppose you have a material like this and you are putting stress in this direction, stress in this direction, and one is in top, like 1, 2, 3, 1, 2, and 3. So stress in this direction will increase this length. Okay. And what will be the effect? This direction and this direction will be also affected because of Poisson ratio nu. So if sigma 1 is there, if you are putting sigma 1 in this direction, so this sigma 1 will induce a stress in this direction also and in this direction also. And that is that the effect of that is effect of that two are here, these two applicable to this one also. If you are putting a stress in this direction, so this length will change, means this will deform. So when this is going to deform, this will be affected and this one will be also affected. So sigma 1 and sigma 3 will come. That effect of sigma 1 and sigma 3 will come. So when you are writing sigma 2, so this will be sigma 2 by E minus nu by E into sigma 1 plus sigma 2. And why I'm writing minus here? Because when you are increasing one length in one direction, because of volume consistency, this dimension should reduce and this one should also. This one should also, because once if you are increasing the length, your width or thickness should decrease because of the volume consistency. Like suppose this is the bar and you are increasing the length, so volume should be same. So when you are increasing the length, this thickness we should reduce to this. So same, that's why this minus is coming. And sigma 3 will be, epsilon 3 will be sigma 3 by E minus nu by E, sigma 1 plus sigma 2. So these three are the strain in three direction due to sigma 1, sigma 2, and sigma 3. E is the Young modulus, nu is the Poisson ratio. So when Poisson ratio, when we are talking, so Poisson ratio is the strain in lateral direction divided by lateral, I'm writing here lateral, divided by strain in longitudinal direction. Okay, minus. So this is the mu. Okay, so strain minus sign is just telling when one direction is increasing, the opposite direction will reduce, means opposite dimension will reduce. Okay, so nothing else. So generally nu is ratio, strain ratio sigma 2 by sigma 1 we are writing, and this is one is the lateral and one is the longitudinal. Okay. So, and minus sign is just telling the direction. Now we are coming back to some kind of energy. Suppose we have a material and this material is deforming. This material is deformed and this is becoming like this. How this material is deforming? Why this is deforming? Because we are putting some stress over here. Suppose we are putting some load, and because of this load, the length is increased up to this. Okay, length is increased up to this. So how much work we are doing in this material? P into L. If this is a gradual loading, this will be half P into L. This is the work done which we are doing on the material. So this work done is nothing but the energy which we are putting to the material. This is the energy. So because of this energy, the material has deformed. And because of that deformation, length or width or thickness, whatever has changed. Okay. So because of that deformation and change in the dimension, strain is coming. So strain is purely a geometric parameter, geometric. Because of the dimension change, strain is coming. Okay. So now the concept is there when we are putting some energy, what is that amount of energy required to deform the material, and that limit, the maximum amount of the energy required for safe maximum amount of energy required so that material will not deform. So suppose we were putting P1, P2, P3, P4 like that load on this material. So up to P3, this was not deformed. Plastically, this was not deformed. At P4, this was deformed plastically. Means this all P1 to P3 was in this zone from here in this zone. And when we are crossing this point, this plastic deformation is starting. So all these are safe. Okay. So I just want to find out what is this limit. So one way to find out what is the strain energy input. So strain energy is one of the very important parameter to find out all this energy failure theory. Strain energy. Okay, strain energy. So what is strain energy? So strain energy, if you have a basic fundamental idea about this thing, work power, like what is the work or power or energy. So you are knowing half epsilon into E into volume. This is the strain energy. Okay. If you are not knowing, we can just derive this here. So why strain energy is coming force into displacement. Okay, force into displacement. If gradual loading is there, half into force into displacement. So change this and this in terms of stress and strain, stress and strain. So when you are putting this in terms of stress, and when you are putting this term in a strain, so this one is delta L. If L was the length of a material, so how much it is increasing? So this is the delta L. If you are putting delta L by L, this will become a strain. Okay. And if you are dividing with this one P by A, so just P by A, this will become the stress, and you just multiply with A over here also. And you have divided L here, so multiply L here also. So this will become volume. So this is going to be sigma in 1 by 2 into stress into stress in strain into volume. So this is coming from this. You can do this just by equating the unit and dimension. Okay. So this is the strain energy. Now, what is this sigma? What is this epsilon? So what is this is epsilon and what is this sigma? We have to check. Okay, this epsilon and this volume we are knowing. Volume, whatever bar or metal specimen is there, the volume of that specimen. So this sigma, if we have sigma 1, sigma 2, and sigma 3 in 3 direction, so definitely there will be epsilon 1, epsilon 2, epsilon 3 in 3 direction. Because if I am telling we have a block like this, so in all 3 direction we are putting a stress 1, 2, 3. So this will induce stress in this direction also and this direction also. So a strain will come in this direction also. So, and this in the previous slide we discussed this thing, epsilon 1, epsilon 2, epsilon 3. So strain energy, when we are writing total strain energy in this body, so that will be half epsilon 1, sigma 1 into epsilon 1. I am taking volume outside plus half epsilon 2, sigma 2 into epsilon 2 plus half sigma 3 epsilon 3 into volume. This is the total strain energy in the body. If we are putting sigma 1, sigma 2, sigma 3. Okay. Now, and this one is also written. Sometimes people are writing energy density. So this is denoted by E, and when we are writing energy density U equal to nothing but E by volume. So simply just take this volume this side, you will get E. So U is sometimes written as 1 by 2 sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3, like that. Okay. And in terms of tensor, if you want to write sigma ij and epsilon ij. So ij is denoting that this index 1 1 2 2 3 3. So this is the dot product of the tensor. So I at this level I am not expecting from you. You have a concept of tensor and all. So just go with this one. Okay. So now you have energy density. So this is the total amount of energy what we are putting in the body. And now this body is deforming because of this energy. So what is that deformation? This shape may change something like this, or maybe this shape will remain same and this will deform length, width, and something. So two things will happen to this body. Either shape of the body will change, shape change. Okay. And another one is size change, size change. So what is these two things, shape change and size change? Means, suppose you have a sphere and you are putting pressure from each side like hydrostatic stress and all. So this sphere will shrink like this. So what is happening here? Initially diameter was D1, big, and now a small d. Okay, so big D to a small d, but still it is a sphere only. So your shape is same, only size is changing. So here size change, here shape is same, shape is same. Okay, so this is one concept. Another concept, shape change. Suppose you have a sphere and now this is becoming a flat surface. So sphere to flat. So this is nothing but your shape change. Shape has been changed. So because of this energy, these two things will happen. Either this material will shape will change or size will change. Means these two things will happen. Shape change plus size change. So this energy has two effects, shape change and size change. Two effects. So whenever we are putting some amount of energy U density, this is going to shape, change the shape plus change the size. Change the shape plus change the size. Okay. Now, from here, our distortion energy is coming. Size change means whatever size initial size was there, same size should be there. So it means you have to apply hydrostatic stress on the body so that the size will change, otherwise it will deform. So any component which is like suppose you have a object like the sphere, and at every point that applied load is perpendicular to the tangent, then only the size will change. At any point, suppose that applied load is like this, it's not perpendicular perfectly, so one component will be in this direction and one component will be in this direction. So this component will try to deform this material in this direction. So this shape will change, means this will become something, this will deform like something like this will go in this direction, so this will become something. Okay, so whenever any component of the force is in the shear direction, material shape will not be consistent, shape will change. Otherwise, if this P is always perpendicular to the tangent of this sphere, it will be always like size, only size will change. Either it will shrink or expand. Expand means if it is pulling. So distortion in the material is coming only because of shear. Only because of shear. Okay? Means distortion. Distortion word, it means your shape is changed. No, your shape is changed. Okay, shape is changed means material has distorted, shape is changed, shape. Okay, so suppose it was a sphere, it may have become some flat circular disc, or if you have a cube, maybe it has become some random shape and all. So whenever this concept is coming, distortion, your shape will change. It will not remain constant, and size change is only because of the hydrostatic. And whenever we are talking hydrostatic, means pressure, hydrostatic pressure means the amount of force you are putting everywhere, it should be same. Then only hydrostatic deformation will occur. Okay, so suppose you have sigma 1, sigma 2, and sigma 3, these three. So hydrostatic stress will be average of these three, sigma 2 plus sigma 3 by. So now what energy we were talking, U is having two part, one is distortion and one is hydrostatic, and distortion is changing the shape, hydrostatic is changing the size. So this energy will cause only size change, and this energy will cause only shape change, and this is purely due to shear, and this is purely due to hydrostatic pressure or hydrostatic stress. Okay, so now if I want to calculate what is this value, so how to calculate? We have this, we have calculated this, where from where? Here you can see this one. So if somehow we are able to calculate this, we can calculate this also. How? U minus UH equal to UD, correct? So now how to calculate this? So it's very easy to calculate UH. So UH we can easily calculate, like we calculated U equal to, total U equal to 1 by 2 sigma 1 epsilon 1 plus 1 by 2 sigma 2 epsilon 2 plus 1 by 2 sigma 3 epsilon 3. It was there. Now we just, oh, sorry. Now we just have to replace this sigma 1, sigma 2, sigma 3 with the sigma p. And sigma p is sigma 1 plus sigma 2 plus sigma 3 by 3. So you just replace sigma 1, sigma 2 and sigma 3 with this. Now our sigma 1 equal to sigma 2 equal to sigma 3 equal to sigma p in case of hydrostatic. So this total energy calculation will become image. So what is to be done now? We just have to replace this 3, 1, 2, 3 with this. Okay. What about epsilon 1, epsilon 2, epsilon 3? So we know epsilon 1 equal to sigma 1 by E minus nu by E into sigma 2 plus sigma 3. Similarly, you are going to write epsilon 2 and epsilon 3 also. And this is sigma 2 by E minus nu by E, sigma 1 plus sigma 3, and here sigma 3 by E minus nu by E, and here sigma 2 plus sigma 1. So now again, we have to replace this, and this, as well as this one, and this one with this 3. These 3. And in this one, you can say sigma 1, sigma 2, sigma 3 are there. So again, you have to replace this sigma 1, sigma 2, sigma 3 with the sigma p. Okay. So once you will replace all this, and if you will put all this value over here, what you are going to get? Just put all this value, then you are going to get 1 by 2e, okay, sigma h square plus sigma h. I am writing like here sigma p is there, na? Hydrostatic, we can write sigma h. Sigma h square plus sigma h square plus sigma h square minus 2 nu sigma h into sigma h, means sigma h square plus sigma h into sigma h plus sigma h into sigma h. Okay, all these things. And once you will solve this, you are going to get the final 1 3 by 2 into 1 minus 2 nu by E into sigma h square. Final expression will be this. After putting the value of epsilon 1, epsilon 2, epsilon 3 and sigma 1, sigma 2, sigma 3 in this equation. In term of in term of sigma h. So you have sigma h, E and nu. Only these 3 parameters should be there in the final equation because everything has been replaced. Okay. So this is the hydrostatic strain energy in the body. And what is this is doing? This is going to change the size. Not shape. This is purely size. Change the size. Now suppose we have to calculate what is the UD distortion. So this simple, and this is purely due to shear. That again and again I am repeating this, purely due to shear. So now you just subtract this and get the what is the value. Just subtract this and get the value. So once you are putting all these things, so in the equation, final means you have u, and you have u equal to what? U equal to 1 by 2e, 1 by 2e, okay, and sigma 1 epsilon 1 plus 1 by 2e sigma 2 epsilon 2 plus 1 by 2e sigma 3 epsilon 3. This is u, and u h equal to, we have calculated 1 by 3 by 2, 1 minus 2 nu by e sigma h square. Now ud equal to u minus uh, and if you will put this value, the final expression, just this is calculation, nothing else. There is no concept, only mathematical expression which you have to solve. So 1 plus nu by 3e into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. This one. This is the final expression. One thing I want to tell, everywhere we have taken sigma 1, sigma 2 and sigma 3, not sigma x, sigma y and sigma z. Why? What is the difference? These three are the general state of stress. General in any direction, x, y, z, in any direction you can take. But this one is the principal stress. State of stress is the principal one. Here the in the principal plane you are knowing there will be maximum stress, normal stress, and in that plane there is no shear component and all. So this all derivation what we are doing is for the principal stress, not for general. If we are doing for general, this calculation will be little bit more complicated, because in the general plane there is tau xy, tau yz, and tau zx is also there. Okay, so this term will also come. So we have not derived till now, we have not derived for this condition. We have derived for sigma 1, sigma 2, sigma 3, and in this plane tau component is 0. So our calculation is simple. You can try with this. You can try with this. While calculating the total energy, you must consider the shear strain also. And when you are considering the shear strain, so energy due to shear component, you have to add in this one, nothing else. Same thing, everything is same. Just you have to add energy due to shear component. Okay. Now coming back to our distortion. So we have now derived this. This is the energy required to distort the material plastically. So this much energy if you are putting in the material will deform, distort, and it is going to deform plastically. So plastically means the some that energy is creating this energy is causing some amount of yielding in the material, so that yield stress will cross this limit and material will deform. So if this amount of energy is causing this much strain, this much stress in the material, definitely material is going to deform, because this is the limit. So suppose we have sigma y is the yield point, and see this yielding in all the direction, 1, 2, 3, all directions, sigma 1, sigma 2, and sigma 3. This all direction is going to be equal to sigma y. Suppose this is going to be sigma y. So material is going to deform now, because this is the limit. So once you will put sigma y at every point of this, what is going to happen? Sigma y. So this will give the limit for distortion. Means material is going to fail, limit. So UD will become now what? Now UD is going to become, we wrote 1 plus nu by 3E. Okay, and here it was sigma 1 square. So sigma y square plus sigma y square plus sigma y square. Okay, minus here it was sigma 1 and sigma 2. So sigma y into sigma y, it will become sigma y square plus sigma y square plus sigma y square. Okay, sigma y square. Okay, but we are making one mistake. What is that mistake? When we are telling deformation, so we are telling uniaxial deformation, uniaxial tensile or uniaxial tensile test or uniaxial deformation. So we have sigma 1 and sigma 2 and sigma 3 in uniaxial is not there. So this value will become 0. Sigma 1, only sigma 1 will be there, sigma 2 and sigma 3 will be 0. So here what was that? Sigma 1, sigma 2 was there, sigma 2 and sigma 3 was there, sigma 3 and sigma 1 was there. So this will be 0, this will be 0, and this will be 0. So this whole term will become 0. Now here it was sigma 1. So sigma 1 means in one direction only yielding is there. Here it was sigma 2. This will become 0. This will become 0. So we have only 1 plus nu by E into sigma y. Sigma, here it was 3. Sigma y square. Okay, sigma y square. Okay, so this is the yielding this is the energy required for the yielding the material. Okay, now this is the final thing what we are getting. If now the concept is, if this energy, this much energy we have put in the material is going to deform in the uniaxial direction. So if this amount is equal to this amount, what will happen? Material is going to deform. So we can get the condition for yielding. So suppose the 1 plus nu by 3E sigma y square is becoming 1 plus nu by 3E. And whatever that value is there, sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma 3, sigma 1. So this will be cancelled. So sigma y, here from here we will get the condition sigma y square equal to this value. So this one, this whole term. So this whole term, if you are going to give, so this will be sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Correct. So this value, whatever we are getting, sigma y, if you square, if you remove it, here it will be on square root. From here I am removing the square. So this side, sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Here this will be 1 by 2. Okay. So we'll just little bit, we'll do more simplification. So this will become sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 1 whole square. Sorry, sigma, okay, sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. If you will do the simplification, this will give like this by 2. And this is the square root. This is the condition for the yielding. So this condition what we derived is for uniaxial deformation. In the case of distortion, just don't forget, in the case of distortion, distortion means due to shear only. And due to shear means this criteria was given by von Mises. This is the name of the scientist, von Mises. So this criteria was given by the own message. So own message is telling if your principal stresses in the material are sigma 1 and sigma 2 and sigma 3. So if principal stresses are this and in uniaxial tensile, your yield point is this sigma y. So if sigma y is equal to or less than this value, your material is going to fail. This was the theory of failure given by the one message. If sigma y is greater than this value, material will not fail. Okay. Is it clear? I hope this is clear. So this is in the three direction. Three direction means you have sigma 1, sigma 2, sigma 3. Now in case of plane stress condition, so when we are talking plane stress, we have sigma 1 and sigma 2 only. Sigma 3 is not. So in the case of plane stress, this is not there. So what next? We will derive it for plane stress. So we will derive it for plane stress condition. So our final equation is sigma y okay, I'm taking a square this side, sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3. So sigma 3 is 0, so sigma 2 square only, plus sigma 3 minus sigma 1. So sigma 1 is there, sigma 3 is 0. So this will become sigma 1 square. Okay. When we are solving this, what we will get? Finally, we are going to sigma 1 square plus sigma 2 square plus sigma 1, sigma 2. This one we are going to get. Okay. For a given material, this is the constant. For a given material, yielding is constant value. There is a certain amount of stress. After that, material will fail. So here we have sigma 1 and sigma 2 as variable, suppose x and y. So this equation will become x square plus y square plus x into y. And this is going to be some constant, suppose r square I am taking. And this is the equation of ellipse. And this ellipse is going to be something like this, suppose this one. Okay, suppose this one is sigma 1 and this one is the sigma 2. This is the sigma 2. So all the value, whatever is inside the ellipse will give the safe condition and outside the ellipse will give the dangerous, that will be dangerous for the design, means that will fail. Okay, that is the condition. Okay, so now we have derived this sigma, we have derived for distortion energy theory, and we calculated sigma ud is the energy density due to distortion, and then we calculated sigma y yield condition, and we derived this thing, that shape of the failure. Okay, so now we are going for pure shear. So in the initial, before this, whatever energy we were giving, that energy was having energy has two part. One was the hydrostatic and one was the distortion. And because of the distortion, we were the shape of the material was changing, so it was distorting, and we calculated what is the expression for this. We calculated expression for this one also. First we calculated this, and then we subtracted this from this, and we got ED. Okay. And this was due to the shear only, and this was due to the normal stresses only. So there is always two component. One is normal and one is shear. So suppose this is on this plane, if you are talking, one is normal and one is shear. So due to shear, there is always distortion. Due to normal, there is a hydrostatic condition. Okay. So I hope this is clear now. I hope this is clear now. So now the condition is, suppose there is a pure shear. So in the same case, suppose there is a pure shear. So in the case of pure shear, sigma, what will be, if we have sigma 1, sigma 2, and sigma 3. So if you have studied the condition of the pure shear means only your material is experiencing this part, like this. Okay, material is having this type of state of stress. So even there is pure shear in this plane, and in this plane there will be a tensile stress. There will be a tensile stress even in this condition. So the thing is that what is the maximum value of the tensile stress in this plane and in this plane, these two. Okay, so if you will put that all this condition, so your sigma 1 and sigma 2 will be equal and with the minus. So what is happening? This direction, there will be tensile, because see, we are putting a stress in this direction, a stress in this direction. Stress means here, and in this direction, and in this direction. And this will be compressive. So whatever amount is coming in this direction, this tensile, and in this direction, it is compressive. So in this plane, if you have studied the maximum shear theory, so you will get the maximum shear stress value will be sigma 1 equal to sigma 2 and minus value. And this will be also equal to sigma 1, 2, and this will also be equal to sigma 1, 2. Okay. So if you will put all this value in the effective stress, or you can say yield. So this one sigma 1 square, it was there, and plus sigma 2 square, was there, sigma 2. So sigma 2 is also sigma 1, and then plus sigma 1 into minus sigma 1. Correct? So this will become what? Here I'm putting a square. This will become sigma 1, 2, 3. Okay. Root 3 sigma 1. Root 3 sigma 1. This will be the effective stress. Okay. Effective, and this is nothing but your maximum value. Okay, so this is nothing but tau x, tau max. Root 3 into tau max sigma y. So in pure shear condition, means you are putting only shear stress. So only shear stress like this. Okay, only shear stress in plane stress condition. Then your deformation means yielding point will give this condition. Your maximum shear stress, whatever value you are giving, into root 3. If this value will exceed yield point, then deformation will occur. And this value give nothing but what? 0.577 into tau max equal to 1 by root 3 sigma y. And this is the condition of maximum shear stress theory. Means amount, how much, what will be the condition for failure when you are putting only tau. So this will give 0.577 into epsilon y. So you might have remembered this formula, but this, from where this is coming, I just explained. Okay, I hope this is clear. And yeah, I hope this is clear, and I would like to go again. Means I was just thinking to explain maximum shear stress theory also, and that is Gusset and Tresca theory. And for all this theory of failure, I just wanted to draw the shape of different theory of failure, like hexagon and ellipse and all. So we will do that one also in the next class. And I hope once this all theory of failure is clear, then solving assignment will be easy. And for me also, it will be easy to explain because you will have already some background. So I just wanted to take one class to explain the distortion energy theory, what I did now. Next class we'll see, we'll solve some problem and we'll see if other theory of failure is coming to the assignment or not. If it is coming, we will solve. Again, we will drive that thing. Otherwise, we will move. We will move forward for the assignment with the assignment. Okay. So I hope everything was clear. We will see in the next class. Thank you.